today in class you played the Making Purple game, which involves spinning these two spinners, and you eventually made a sample space to show all the different things you could spin when you spun the two spinners. And you ended up with 9 total outcomes. Now, you don't necessarily need to draw a sample space to figure out the total number of outcomes of an experiment. You can use what's called the counting principle. If there are 3 different things we could spin on the first spinner, and 3 different things we could spin on the second spinner, if you multiply those outcomes, 3 times 3 is equal to 9, and that gives me the total number of outcomes. So, for example, if I was doing an experiment that involved rolling this die and then flipping the coin, I don't need to do a tree diagram or a list to see all the outcomes. On the die, there's 6 total outcomes. On the coin, there's total outcomes. So if I multiply those, in my tree or my list, I should have 12 total outcomes for rolling the die and flipping the coin. The other great thing about the counting principle is that it also helps us calculate probabilities. You found the chance of making purple, of spinning red and blue on the 2 spinners, happened this 1 time out of 9. Probability of red, blue was 1/9. But I can figure that out even without the tree. I can say the probability of spinning red on the first spinner is 1 out of 3, and the probability of spinning blue on the second spinner is 1 out of 3, and if I multiply those 2 probabilities together, I get my total probability. And this is called the multiplication rule. Now, the spinning of the 2 spinners in the Making Purple game are considered independent events because what you spin on the first spinner has no impact on what you get when you spin the second spinner. So our multiplication rule then tells us the probability of these 2 events, A and B, happening together can be calculated from the probability of event A times the probability of event B. So just as a side example here, I'm going to go back to my dice and my coin. If I wanted to figure out the probability of rolling an even number and then flipping heads, I don't need the tree or the list, my sample space. These are 2 independent events. The die has nothing to do with the coin. So my chance of spinning an even number or rolling an even number on the die is 3 out of 6, and my chance of flipping heads is 1 out of 2. So my total probability is 3 out of 12, or 1 out of 4 if you reduce. So theoretically, if I were to do this experiment 12 times, I should get an even and a head 3 times out of 12. So now let's apply this to the Price is Right big wheel. We want to figure out the probability of spinning $1 and spinning $1 again. Well, the chance of spinning the dollar on the first spin is 1 out of 20. There's only 1 space out of the 20 that's marked $1. And then my probability of spinning it again is the same. There's only one $1 spot. And if I multiply those together, I have a 1 out of 400 chance of winning the $11,000. Now, sometimes the outcome of the first event can affect the probability of what happens on the second event. This is the case in the Let's Make a Deal spinner at the bottom of your page. We want to figure out the probability of spinning the car and then spinning a car the second time around. Now, the first time, 2 spaces out of 8 are marked car. But once you spin one of those cars, it is gone, and it becomes a zonk. So now when you go to spin the second time, our probability is not the same. We still have 8 spaces, but not two of them are cars, only one of them is a car. So when we multiply 2/8 times 1/8, that gives me a probability of 2/64, or 1/32 if we reduce. And how this looks in terms of A's and B's is the probability of A and B, both things happening, is equal to the probability of A times the probability of B given A has happened. So make yourselves a little note here that this funny notation with the B, with the line between it and the A, is the probability of B given A has happened or occurred.